Okay, here I've got a composite beam made of aluminum and brass. Okay, basically I want to figure out um, what moment they can handle given the bending stresses given there for brass and aluminum. Now, when I have a composite beam, okay, since they've got different properties, what I do instead is I treat it as if it, like hypothetically treat it as it's the same property, which is to say, I need to go look up what the Young's modulus is for each one, and I looked that up for aluminum. Young's modulus is 68.9 megapascals. And for brass, I look up and I see that the modulus is 101. Oops, not megapascals, gigapascals. Excuse me. Let me correct that one. This should be gigapascals. Okay, so because brass is bigger than aluminum, the way that I like to do is I always like to make my hypothetical guy in terms of the aluminum, the smaller one. So what I do is my cross section will now look like this, okay, where it's all made out of aluminum, okay, and the bottom is still 150, but then the top, because E is larger for the brass, I'm going to extend the size of that, okay, times where I take basically 150 times N, where N is the ratio, not M, M. N is the ratio of the moduli. So that's going to be 101 over 68.9, where N then is 1.466. Okay, so I take 150 times 1.466, so the equivalent would be 219.9, right? So if the whole thing was made out of aluminum, okay, that top piece would have to be about 220 millimeters to have the same um, properties, bending properties of brass, which has a higher E. That higher E makes it stiffer, so I equivalently make it wider if I was going to make it out of aluminum to make it stiffer. So again, this is all hypothetical kind of things so that we can solve the problem. So I just hypothetically make it all out of aluminum because brass is stiffer. I need to make it wider. I make it wider by the ratio of the E's like that, where I've got the 220. So again, here is 50. Oops. This height is still 50. This height is H. And I want to find H so that the neutral axis is at that seam. So I'm going to go through the process of doing that. So I want the neutral axis at 50. Okay. So I'll start with the lower piece, the lower rectangle. Its location is its centroid's at 25, and that's going to be 50 times 150. Okay. And then the other guy's height is going to be 50 plus h over 2, right, the midpoint of that h. Okay. Then times the width, 219.9 times h. Okay. And then that's divided by the total area, which is going to be 50 times 150 plus, I guess that would just be times 219.9 times h. From all of that, I learned that h then needs to be 41.3. So it's not really drawn to scale. However, okay, that is what h needs to be. The height of that brass needs to be that, so that the neutral axis would actually be at the seam there. Okay. Okay, so now that I know that, okay, again, I'm looking for the flexure formula, which is mc over I. So now effectively I found my C values. Okay, M is what I'm ultimately looking for. The bending stress is given to me. I just need to find I now. Okay, and I'm going to do I of that new hypothetical cross section that I've got. So we'll start with the base, which will be 1/12 times BH cubed. Okay, and then parallel axis will be plus the area, which will be 150 times 50, and then the distance from the neutral axis. And the neutral axis is going to be at 50, right? Because it's right at that seam there. So the distance away is just going to be 0.025 squared. Okay. To that, I need to add that top one, which is going to be 1/12 BH cubed, where B is 219.9. H is the 41.3, so BH, oops, I need a 0 in there. Cubed plus the area, which is just 2199 times 0.0413, okay, times that distance, okay, which is just going to be half of the 413. And then that will be squared like so. Okay, so this is I of this hypothetical all aluminum thing here. And again, we do that because I need to get it all made out of one piece. So I just pretend the brass is aluminum, make it a little bit bigger because the brass is stiffer, and so on. From that, I get that I for this is 11.4 times 10 to the minus 6. Okay, now from that, what I want to do is I need to find using the flexure formula, which of course is sigma equals mc over I, but I need to multiply it times n, at least when I do the brass. For the aluminum, I leave it alone, right? So for the aluminum, it's 128 megapascals. So I go 128 times 10 to the 6th equals mc over A. Now, aluminum's on the bottom, so the C I use is going to be 50 on this one. So it's going to be m times 50. Nope, I need a 0 in there. All over I, which I just calculated to be 11.4 times 10 to the minus 6th. From that, the moment necessary for the aluminum to reach its allowable bending stress is 29.2 kilonewton meters. Do the same thing for the brass. The brass is 35 megapascals. Okay. This time I need to take it times that N, right? Because now I'm converting back from the aluminum to the brass, so I need to multiply it times the N. Okay, and then that's going to be mc over I, where C this time, again, because it's brass, is that top one. That's the 41.3. I is the same. Okay, and again, I put the N in front of this because I'm looking at brass, even though hypothetically I was looking at all aluminum. So I need to basically go back to, okay, well, now let's say this is brass. I need to multiply it then times that N, which I didn't have to do when I was using it as aluminum. The other thing is noticing brass is on top. I have to use the H, which is 0.0413 rather than the 0.05 that I used for the aluminum. I will remain the same. Obviously, the sigmas are different based on the thing. But from this, I learned that the moment for brass to fail is 6.59 kilonewton meters. Now, that's my answer because it's smaller, right? I'm trying to find how big I can get before it breaks. I'll never be able to break the aluminum. The brass will break first. It's the limiting factor. So that's the answer that we choose.